Okay, now it's recording. Okay, it's recording. Okay, so let's begin. Okay, so wait, let me see. Okay, the sound is recorded. Okay, right. So okay. So a 5 mm thick copper plate is sealed to a 10 mm thick aluminium plate, and both have the same cross-sectional area of 1.5 meters square. The outside face of the copper plate is 100 degrees Celsius, while the outside face of aluminium plate is 60 degrees Celsius. Knowing that the heat flow is steady and no energy is lost to the surroundings, determine the temperature at the copper aluminium interface. Okay. So what does it mean by this question? Yeah. All right. So let me explain. Okay. So here we have two items. One is copper and the other one is aluminium. And here he mentioned about the thickness. Okay. So this is actually the the delta L. Both of these are the delta L. Okay. And these are the cross-sectional area A, and the outside face of copper plate is 100. Okay, this is the temperature at one end, and outside face of aluminum is 60. Okay, so maybe you don't understand this, so let me draw it out. Okay, let me draw it out. So we have okay, so here this one you can see this is the copper plate. Okay, this is the copper plate, and another one you have aluminium plate over here. Aluminium plate. Okay, so thickness, this is the delta L. Okay, delta L, which is or we can say it is a 5 mm. Okay, and then for aluminium the thickness is 10 mm, the delta L. Yeah, this one you need to change to SI unit later lah. Okay, cross sectional area, okay, 1.5. Okay, so it's given there, cross sectional area. The cross sectional area, the cross-sectional area is 1.5 meters square. Yeah. So outside face of copper is 100. That means outside. We can say this is the outside. Yeah. Out here is the outside, and this one also the outside of this part is outside of copper, and this part is the outside of aluminium. Understand? So outside of copper is 100 degrees Celsius. So here is 100 degrees Celsius, and then the outside face of aluminium is 60. So here is 60. So heat actually flow from the hot temperature passing through the interface and then going to the aluminium. Yeah, from copper go to aluminium. Understand? Heat always flow from high temperature to low temperature. Okay, heat always flow from high temperature to low temperature. And he say that here you can see the interface, isn't it? The interface. So this is the interface means here lah. This is the interface. The interface. Okay. Joining copper and aluminium. Yeah. Here you can see he say heat flow is steady. What do you understand about heat flow is steady? Do you remember what I mentioned about heat flow steady? Steady heat flow. Steady heat flow means what? Still remember what is steady heat flow? Did I mention anything about steady heat flow? Maybe forget already. Never mind. Steady heat flow means the heat flow earlier part equal to the heat. The steady heat flow means the heat flow is constant all through the whole metal. Or if we see heat flow is steady, it also means that these items are insulated. They are insulated. Okay, that means no heat loss through the surroundings. They are all insulated. Yeah, steady heat flow means the heat flow is constant. Why the heat flow is constant? Yeah, heat flow constant from hot temperature to low temperature. Because it's insulated. Insulated, so there is no heat loss. The heat cannot flow out. No heat loss to the surrounding. No heat loss. So when we see the word, the heat flow is steady. Heat flow is steady. It means what? It means first, it means the heat flow is constant. The rate of heat flow, rate of heat flow is constant throughout the whole metal. Okay, and no heat loss. No heat loss to the surrounding. The metal is insulated. The metal is insulated. Achieve steady state of heat flow. Sometimes we say steady state. Okay, so it also means that the heat flow at copper same as heat flow at aluminium. So we can write heat flow, the rate of heat flow at copper equal to rate of heat flow at aluminium. Do you know why the heat flow is equal in copper and aluminium? Do you know why? Class?
Because steady.
Yeah, because he said heat flow is steady. Steady state means the heat flow is constant through the whole metal. Through the whole metal. That means no heat loss to surrounding. No heat loss to surrounding. And why no heat loss to surrounding? Because insulated. Is insulated. So the heat flow at copper equal to heat flow at aluminium. Imagine if this metal not insulated, then heat will loss in the middle. Yeah, heat will loss. Someone joining. Okay. That means heat will loss in the middle, and so the heat flow at copper is not the same as heat flow at the aluminium. That means heat flow at copper must be more than heat flow at aluminium. Understand? But now because it's insulated, no heat loss to surrounding, so the heat flow is steady, or that means heat flow is constant through the whole metal. So we can write heat flow at copper constant to heat flow at aluminium. The rate of heat flow at aluminium. Understand? Or we can say the power at copper equal to power of at the aluminium. Okay. Okay. So we are going to use this formula to to do these questions. Yeah, we're going to use this formula to do the questions. Understand? Rate of heat flow. So okay, let's copy this and we will do over here. Okay, so now let's start. Let's start. So question A. So we want to find the heat flow at the copper aluminium interface. We want to find heat flow at the center. We already know heat flow at copper outside surface and aluminium outside surface 100 to 60. So what about the middle? We want to find the heat flow at the interface. Just put T lah. Just put T like that. Okay. So we know that if you want to find initial and final, we can say this one is T initial, T final. And then this one for copper, 100 is initial, and then the joint temperature, the interface temperature is the final. For aluminium, the initial temperature is the joint temperature. This is the T initial, and then the 60 is the final. Correct or not, class? Initial, final, initial, final. Understand? Okay, so let's do it. Yeah, and then we substitute what formula? What formula do we substitute? Remember the this one heat flow is the same, steady state. Yeah. So what formula we're going to use? This formula, QOT equal to negative Ka delta T over L. This one. Yeah. So substitute that formula into it. So negative Ka delta T over L for copper equal to negative Ka delta T over L for aluminium. Like that, yeah. Now we can area is the same. Area is the same, so can cut off the area. Negative also no more. So we have here we have K for so here we have K for copper, K for aluminium. So can substitute. Copper is 400. Copper is 400, and then okay, what is the delta T? Delta T, we always take final minus initial. Final temperature minus initial. The copper is T minus 100. T is the final minus 100 initial. Initial high temperature, final low temperature, isn't it? And then delta L, 5 millimeter. 5 millimeter. So 5 change to SI unit, negative 3. Milli is negative 3. Okay. And then aluminium is 200. Aluminium is 200. Multiply with final is 60 minus T. 60 minus T. Divide by what is the L? 10 millimeter. 10 millimeter. 10 exponent negative 3 meter. Okay, so that's it. So we can calculate the T. Let's calculate. Okay, someone calculate. You certainly get what answer. What answer do you get? Let me check the answer straight away. Yeah, let me check the answer straight away. The temperature should be chapter 8, right? So it's 92 degrees Celsius. It's 92 degrees Celsius. Temperature is 92 degrees Celsius. Okay, that's how do you get the temperature at the interface. This is the temperature at the interface, the joint temperature, or you can say interface. Sometimes we say it's a joint temperature. Sometimes we say it's interface temperature. It's the same, yeah. Joint temperature. Okay, that means temperature at the middle. Temperature at the middle. So we know that at the middle is 92 degrees Celsius. Understand, class? Give me a thumbs up if you understand. Yeah. Okay. Yeah. So that's it. So that's the temperature at the middle. So you can only do this question if it is insulated and can achieve steady state, constant heat flow. Then the heat flow is constant for copper and aluminium. Then only can find the joint temperature. If heat flow is not constant, is non-insulated, heat flow got heat loss, then this question cannot do. Yeah, the question must be steady heat flow. Yeah, can achieve steady state first. Then only can do this question. Yeah, no heat is lost. See, no heat is lost to the surrounding. Why no energy is lost to the surrounding? Because insulated. Because the metal are insulated. Okay, class. Now, rate of heat flow through the cross-sectional area. What's the rate of heat flow through the cross-sectional area? That means we want to find what? Rate of heat flow means QOT lah, isn't it? Rate of heat flow. So we can either use copper or we can also use aluminium. You want to find this Q over T, you can use the copper or aluminium because both are equal. Both are equal. Yeah, both are equal. So let's do it. So depend lah. Your practical session you want to do online. Online will be like this. Yeah. If you want to do face to face, then we do in face to face. Yeah. So you give response on the poll there. Okay. So if you don't do online, yeah, if I have conducted the same lecture for other class, I just share the same video, yeah, for the next class. That's the reason actually. Okay. Anyway, yeah, depend. Okay, so rate of heat flow for copper, you can you want to find rate of heat flow, you can either use copper or you can use the aluminium. Yeah, aluminium. So if you use copper, then you use the copper for negative Ka. The K use the copper, and then delta T over L. This one is for copper. If you use aluminium, then you use aluminium lah. Okay, delta T over L for aluminium. Okay, class. So let's find out. K is for copper is 400. And then what is your A? What is your area? Your area is 1.5. Area is 1.5. And then delta T for copper is 92 minus 100. Understand? Final minus initial. 92 minus 100. Just now you got 92, right? This one, is it? This one, 92. You got 92 minus 100. And what is the delta L? 5 millimeter. 5 millimeter. 5 millimeter, negative 3. So what answer do you get, class? Let me just check the final answer for you. The final answer is 9.6 exponent 5. I get positive value. Yeah, this one must be positive. Negative, and here also get a negative value. Negative, negative, positive. So finally I get 9.2 exponent 5. So what is the unit? Joule per second, or you can put as watt, or you can write joule per second because it's actually power, you know.
9.6.
9.3. You get 9.3, is it?
9.2.
9.2. So which one? Never mind lah. Almost the same. Yeah. Yeah. 9.3. Or 9.6. Oh, okay. Sorry. 9.6. Okay, 9.6. Okay, 9.6. Yeah, 9.6 exponent 5 joule per second. Yeah. You do the aluminium. Yeah, aluminium also. This one you substitute with 200. And then delta T. This one you substitute what? 60 minus 92. 60 minus 92. What else? This one, the delta L. This one is 10 millimeter. 10 millimeter, that means 10 exponent negative 3 meter. You also get the same value, yeah, 9.6 exponent, because it's a steady state, constant heat flow. Understand? Constant heat flow, you surely get the same answer. Okay. So that's it for question 5. The next question. Yeah. So this is the same question. Same question 6. It's the same lah, yeah, actually. Two well insulated A and B joined together. So it's steady state. You see, steady state. Whenever you see the word steady state, that means this item, they are insulated. Insulated means no heat loss. As long as you see steady state. Steady state means constant heat flow, no heat loss to surrounding because it's insulated. So constant heat, better is constant rate of heat flow. Constant rate of heat flow. Constant rate of heat. My writing. Constant rate of heat flow. Constant rate of heat flow. Okay, steady state, insulated, no heat loss. Same cross-sectional area. Yeah, they have. This is the same question as question just now. Yeah, the method you do also the same. Yeah, same cross-sectional area. Thermal conductivity of rod A twice the rod of B. Rod of B. Okay. Determine temperature at the joint. That means now he wants you to find temperature at the joint. The temperature at the joint. So that means the temperature over here. So can you do? This is the delta L, delta L. So same way lah. So am I do again? So question A. So you can say the rate of heat flow at A equal to rate of heat flow at B. That means the heat flow is the same, yeah. Because why? Insulated. Insulated. Negative Ka. Wait, this is the K for rod A, area delta T over L. This is for A also. And then negative K, this is for B, area, and then delta T over L for rod B. Okay. So I cancel the area because they have the same cross-sectional area, negative, negative, positive. K. He say the Ka is twice the Kb, isn't it? Ka, the thermal conductivity of rod A is 2 times the rod B. 2 times the rod B. So I can substitute. That means A is a good conductor. A is a good conductor of heat. Yeah. B is what? Bad conductor. Right. B is a bad conductor of heat. Because he say A, the thermal conductivity is twice of B. That means A conduct heat. Good. Very good. B conduct 2 times less than A. Yeah. B conduct 2 times less than A. Yeah. A conduct better. Yeah. Twice the rod B. Okay. So you can just substitute Ka with 2 Kb lah. Okay. Ka you substitute with 2 Kb. Then you can cut later. You see. And then change of temperature, just take the temperature at the joint minus final minus initial. Remember, this is the initial final, and then for rod B, this is initial, this is final. Understand? For A, this is initial, and then this is final, and then for B, this is initial, this is final. So take final minus initial. Final, just put as T. Okay, so T minus 160. And then, okay, class, do I need to change to Kelvin for degrees Celsius? Do I need to change to Kelvin? No need. Remember, I said about this before. For change of temperature, for delta T, yeah, all this delta T, you can either degrees Celsius or Kelvin. Because why? The increase of 1 degree Celsius is the same as increase of 1 Kelvin. Okay, so but for later for temperature of that one you must be Kelvin only lah, yeah. For formula PV, so for following question, PV equal to nRT. That one, the temperature that was must be in Kelvin, yeah. This one must be in Kelvin. For formula this temperature must be in Kelvin. But for change of temperature delta T, if you see delta T, you no need to change to Kelvin. You can maintain as degree Celsius. Like this 160, you can maintain as degree Celsius. No need to change. Yeah. Can maintain as 100 and can maintain as degree Celsius. Okay, now L for A is 25 cm. So change to meter means divide by 100. So it's 0.25. Yeah, 0.25. And then equal to Kb, and then this one is what? 50 minus initial temperature. 50 minus initial temperature, and then final minus initial. and then 55 cm, so 0.55 meter. Okay, I got it. KB and KB can cut, you see, cancel. So you can find the final temperature already. What is the final temperature? Let's find the final temperature. What's the answer? Question 6. Question 6. 140 degrees Celsius. 140 degrees Celsius. So that's the answer. 140. 140. Understand, class? That's the temperature at the joint. So I got the temperature at the joint, which is 140. So the temperature actually start from 160, decrease to 140, and then decrease to 50. See that? Okay. Now, question B. Let's sketch a graph of temperature against distance graph for heat conduction through the rod. That means I want the temperature against distance. So temperature against versus distance lah, versus L lah. That means it will show us the temperature gradient. Temperature gradient delta T over L. Understand? We need to plot a graph for both of these rod. That means graph like this. Graph like where is the graph? Let me see. Oh, sorry. Something wrong with my mouse already. Something wrong with my mouse. That means we need to plot this graph. Some graph for like this. See, if you have two composite, this is called composite rods in series. That means you will see if good conductor, this is a good conductor and this is a bad conductor. Yeah, this one. So you can see this. You need to plot this graph. Plot this graph. You must have values given. So okay, let's find out. Yeah, let's plot the question B for question B. Let's do question B. Okay, question B. Let's plot the graph. So I need yep, like this should be good. Yeah. Okay, so this is the temperature, degrees Celsius. You must have unit, class. You must have unit. And then L is in meter. But if you want to maintain, never mind lah. Yeah, put in meter lah. Yeah. Okay. Now, so from 0 up to 0.25 is maybe over here, 0.25, and then the next one is what? 0.55. That means 25, 2, and then over here, I think. Yeah, over here. So is this 0.55 class? Is it 0.55? Yeah, from here up to here, is it 0.55? No, you must add up. It's wrong. It's not 0.55. You understand not, class? Do you understand? It's not 0.55. It's wrong. It's not 0.55. You must add up 0.55 plus 25, which is 0.8. It should be 0.80. Understand? Because we know that from here to here is 0.55. Understand? Because the first metal is here, first metal, and then second metal. So 0.55 plus 25 is 0.8 actually. Don't get it wrong, because some of you may get wrong. I hope that it's not you lah. Okay, next we need to put value. Okay, 160 up to 140 and then down to 50. So let's plot it. Yeah, we plot the dotted line first. Dotted lines to guide. Sorry. Draw. Okay. Okay. So and then what else? Start from 140, right? No. 160. So start from 160 degrees Celsius up to 140 and then go down to 50 lah. Put like this, yeah. So it start from 0, that means 160 over here. and then go to this point, you know, go to this point already, so which is over here, and then after the second rod, the 50 is over here, which is over here like that, right? So okay, the graph is like this. Is like that. Okay, class. So do you see which one has a bigger gradient? Which one has a bigger gradient? You see, class, which one is a bigger gradient? Good conductor or bad conductor? Someone? Bad conductor or good conductor? Which one more gradient? Which one is a good conductor? A is a good conductor because it's 2 times the rod B. You see? The thermal conductivity of A is twice the thermal conductivity of rod B. That means A is a good conductor, B is a bad conductor. So when good conductor, look at here, when K is big, when big K, KB is smaller. So to balance both sides, yeah, when K value is high, the gradient is low. See that? And this one, if K is low, the gradient is high. Understand? Yeah, understand? Give a thumbs up if understand. Yeah. If good conductor means big K, big K. If low conductor means small K. But you must know the rate of heat flow is equal for A and B. So left and right hand side is equal value. So if one partner is big, the other partner must be small. Right or not? If one partner is small, the other partner must be big. Then only can equal both sides. So if good conductor, high K, the gradient is small. That's why you see a good conductor, small K, a small gradient. Bad conductor, low K, big gradient. See, big gradient. So this one is a KA is big, the gradient is small. The gradient for A is small. And then for KB, the bad conductor, a bad conductor has big gradient. Bad conductor has big gradient. It's like that. Yeah, a good conductor, the drop of temperature is small. For bad conductor, the drop of temperature is high. You remember, class, this one? I give one example lah. Yeah, I give one example, like for example, like, you know, remember, okay, maybe I should write something over here. This is good conductor. This is bad conductor. The good conductor, the temperature drop very small. The good conductor, temperature drop is small. The bad conductor, temperature drop is big. I give one example. For example, our cooking wok. Did I explain about this cooking wok before? I don't remember. Yeah. Maybe this one is made of plastic. Yeah, made of glass or plastic, or maybe plastic lah. Yeah, maybe plastic. Yeah. You boil your Maggi mee over here. Yeah. Boil it. Yeah. Boil it. Yeah. So you boil it. Boil. Yeah. Compare to you use compare to you use what? Wait, maybe metal one. This one is a fully metal. Metal. So if you boil it, which one you prefer to use? The plastic gear one or the metal one? The handle is metal. Which one you prefer to use? Which one you prefer to touch? Yeah, to hold. You want to hold which one? You want to hold the plastic one? You want to hold the metal one? Your hand is here. The first one, isn't it? Compared to the second one, right? Why? Why we feel safer to use the first one? Because the change of temperature. Let's say this one is 160 across 160 degrees Celsius. Across the plastic, the gradient is big. Maybe it dropped to 30 degrees Celsius already. Understand? So you feel like it doesn't feel the heat. It doesn't feel it's hot, right? If metal one, the drop is a good conductor. It's a good conductor. So the drop of temperature is very small. 160, maybe is over here is 120. Understand? Go to hold the metal one, you feel hot. Understand or not, class? You understand? So for good conductor, the drop of temperature is so small. So that means for the metal easily get hot. Easily get hot. The whole metal. Because the heat conduction is so good. The heat conduction is so good. This one, the drop of temperature for bad conductor. For bad conductor, the drop of temperature is big. The temperature drop across the plastic very fast. Temperature drop a lot. The gradient is big. The gradient of temperature. The gradient is big. So for plastic, a bad conductor, the temperature drop is big. Temperature drop big, that means you don't feel it's hot. Don't easily get hot. But for metal, it easily get hot because the temperature drop is small, so easily get hot. Like that lah. Understand, class? I hope you get it. So this is good conductor, this is bad conductor. So let's say I change it. Maybe rod A I change to over here, and B I change to the other side. What will happen, class? Maybe let's make it this way. This time maybe B I put it here, A I put it here. So this bad conductor is here. Bad conductor, the KB is a small. Good conductor now is over here. Good conductor. So where do you think what do you think the graph will be? What do we think the graph will be? Temperature against distance. What do you think? If bad conductor this way, then which one has a bigger gradient, class? Which one has a bigger gradient? Maybe 160. It would drop to maybe it dropped to, last time it's dropped to 140 only. This time maybe it dropped to 70. Maybe it dropped to 70, and then finally dropped to 50. Maybe maybe drop. So like that. So the graph will be like this, and like this. So the graph will be like that and like that. Understand? Bad conductor drop fast. Bad conductor has big gradient. A good conductor has a small gradient. This is for A. This is for B. Understand? Understand, class? So that's the difference lah. If good conductor is over here, the gradient is small. Bad conductor, gradient is big. So bad conductor, if you switch side, then the gradient, the earlier part has a big gradient, the later part has a small gradient. Bad conductor, temperature drop a lot. Good conductor, the temperature drop a little bit. Good conductor easily get hot. The temperature drop a little bit. Okay, so it just change the graph. Okay, so be careful. If the question asks you to sketch a graph, you must have all the values available. Don't just sketch and without values. You must label. You see, must label. Label means what? You must have values. Must have symbol. Must have unit. Must have unit all. Must have unit. Must have values, must have symbol T and L. Understand? Okay, so that's for question what? Question 6, question 7. Yeah, question 7. Calculate the temperature gradient for each rod. This is the same lah, the same. So let's do question. Yeah, question. Yeah. A temperature gradient for each rod. Okay, so what is the temperature gradient? Let's find out temperature gradient for each rod. So how temperature gradient? Okay, you see, this is a straight line graph. So we can straight away say this is insulated. Do you know why it's insulated? This also can say is achieve steady state. If the graph is straight line. If the graph is straight line. Straight line. If straight line, we know it is insulated, is achieve steady state. That means we also can say the constant heat flow. The heat flow at m equal to rate of heat flow at n. Because if not straight line, if non-insulated is curve. See, if non-insulated, it's curve. If straight line means insulated. Understand? If non-insulated, the graph should be curve. Okay. If straight line means insulated, and this one, the rate of heat flow can achieve steady state. Rate of heat flow for both materials is the same. Okay. If non-insulated, you cannot. The heat flow for number 1 is more than rate of heat flow for number 2. That's for non-insulated. Okay, but if the like question 7, he said this is a straight line graph. Straight line graph must be insulated. Achieve steady state. That's the first thing you must know. Okay. Now, A, temperature gradient for each rod. So for rod M, we do for rod M first. Yeah, for rod M, so the temperature gradient delta T over L for M is what? Delta T over L for M is 60 minus final minus initial. 60 minus 100 over you can maintain as degrees Celsius. Can maintain as degrees Celsius because I already mentioned delta T can put in degrees Celsius. Okay, the length must be in meter lah. You must change from cm. Be careful. The cm you must change to meter. So it's 0.4 meter. It is 0.4 meter. Yeah, 0.4 meter. Okay, 0.4 meter. Okay, so let's get the answer. What's the answer? Let me check the answer. Where's the answer? Question 7, isn't it? Negative 100 degrees Celsius per meter. So the answer is negative 100 degrees Celsius per meter. Yeah, degrees Celsius per meter. That's the unit for temperature gradient. Okay, and it must have a negative value. Because gradient must be negative. Remember, gradient must be negative. All these are negative gradient. Okay, how about rod N? Rod N must be a smaller gradient. This one is a good conductor. No. This one's a bad conductor. This one is a good conductor, isn't it, class? Remember, N is a good conductor. M is a bad conductor. Okay, so find the temperature gradient. So for N, it will be 40 minus 60 degrees Celsius per, the distance is 100 minus 40, so it's 0.6 change to meter, 0.6 meter. So what answer do you get? So the answer is negative 33.3 degrees Celsius per meter. Negative 33.3 degrees Celsius per meter. Yeah, that's the answer. Okay, smaller gradient. bigger gradient. Okay, if area is the same and temperature at the composite end are maintained, determine which rod has higher thermal conductivity. Which rod has a higher thermal conductivity? Of course, is this one. The N, isn't it? Has a higher thermal conductivity. The drop of temperature is small. Okay, how to prove this? Again, you have to use the method I showed just now. Use the constant heat flow, this one. Yeah, constant heat flow, this one. Do it over here. Okay, that means from here we prove it. Negative km area delta T over L for this one is m negative k and area delta T over L for n. We know that this one has a bigger gradient. This one is smaller gradient. So this one is small. This one is big. See? Oh, is there a value? Yeah. So we can say, delta T over L m is bigger than delta T over L for n. Write the value you found just now. This negative 100 degrees Celsius per meter is bigger than negative. Don't be misled by the negative sign. Misled by negative sign. We don't look at the negative sign. We just look at the value. 100 bigger than 33.3. Just look at the 100. So actually it's like we can say modulus lah. Modulus, we just look at the value. 100 bigger than 33.3, not the negative 100. Yeah, it's just the the gradient is bigger. The gradient, this one is bigger compared to gradient of n. Understand? So if this gradient is bigger, that means the k must be smaller. So we can say k. So k for m is smaller than k for n. Like that lah. Okay. Write it this way. If gradient of m is bigger, so the thermal conductivity of m is smaller. Smaller than n. So n, we can say, conclusion, we can say n is better conductor of heat because the k value is higher, the thermal conductivity value is higher. N is a better conductor of heat compared to m. Okay, class, understand? That's all for today's lesson. Yeah, we still have 3 more questions for chapter 8. I will continue tomorrow morning lah. Yeah, for this one. Okay. So any question, class? Understand everything? Okay, good. Yeah. So okay, see you tomorrow. Yeah, see you tomorrow. Later, I also have other class. I will record the video. That's for chapter 9. Late tomorrow, I will ask you to watch the same video lah. Yeah, which I have conducted for other class. It's actually the same thing. I have to reteach the same thing. So that's why I ask whether you prefer full full online or face to face, because I'm teaching the same subject, same thing again. So okay, give me some response on the Telegram. Okay, thank you. Okay, see you tomorrow. Okay, bye.
Thank you, sir.
Okay, thank you.
Thank you,